In Chapter 2, we developed the concept of a limit and how to work with limits and evaluate them. And the reason why we developed them was we needed it for the definition of the derivative. So as we saw in Chapter 2, calculating derivatives using that limit definition is a fair amount of work. And as I mentioned before, the problems we've done with these calculations have been fairly simple. With a lot of functions, calculating those limits can be extremely difficult, sometimes even impossible. So in this chapter, we're going to learn differentiation rules, and what these are basically shortcuts. So we'll have different rules for different types of functions that will tell you how to quickly find what the derivative would be without even having to use the limit definition. So in section 3.1, we're going to look at two types of functions, polynomials and exponential functions, and we'll learn shortcuts for calculating the derivatives of these types of functions. We'll start with the simplest type of polynomial, and that is just the constant function, which has the formula f of x equals a constant. So we want to find what the derivative is. Before we apply the limit definition, let's just think about it graphically. So we know the graph of this f of x, y equals a constant, is a horizontal line. And if you pick any point on that line and sketch the tangent line would be exactly the same as the blue line itself. And that's the same at every single point. So then, for each of those points where the tangent is horizontal, the next question is, what is the slope of the tangent? Well, obviously, since it's a horizontal line, its slope is 0. And that's true at every point. So that means the value of f prime at every single point is equal to 0. So we conclude f prime of x equals 0 for all x. Now that we know a graphical reason why the derivative of the constant function would be 0, we can actually prove that by using the limit definition of the derivative. So here we've written the limit definition for f prime of x, and since our formula for f of x is equal to c, that means f of anything is equal to c. So this f of x plus h is equal to c, and then this f of x is also equal to c. In the numerator, that simplifies to 0. So we have 0 over h, and that fraction is equal to 0. Now we're taking the limit of a constant, which is always just equal to that constant. So we just concluded f prime of x equals 0. So this is our first shortcut, and we can see it here. The derivative of the constant function using the Leibniz notation. This says the derivative of what's in the parentheses, which is the constant function c. The derivative of c with respect to x is equal to 0. So this is something we will use repeatedly in this course, and then you'll use it a lot in future courses also. So you definitely want to remember, whenever you have a constant function, its derivative is 0. We're now going to work towards finding a shortcut for taking the derivative of a power function. Now a power function looks like y equals x to a constant power, where that power n is a positive integer. So we're going to build our way up. Let's start when n is 1. So now f of x is just x to the first power. We know the graph of that is just this diagonal line with slope 1 and y-intercept 0. Now think about f prime as being the slope of the tangent. If you pick any point on this line and you sketch the tangent, it's just the same as the line itself. And the slope of this line, we just said, is 1. So that means at any point, the value of f prime is 1. And so we have this formula here using the Leibniz notation. Right, so in prime notation, we would say if f of x equals x, then f prime of x equals 1. In the Leibniz notation, we say the derivative of this function x, and then over dx means with respect to x, that derivative is equal to 1. So now we want to build up to higher numbers for n. We just did n equals 1, so we're going to look at n equals 2, 3, 4, and so on, and see if we can generalize about the derivative of x to the n. We're looking at this power function, y equals x to the n. We already considered the case where n equals 1, and we found the derivative. I'm going to add that to our list here just so we can see that. We found the derivative of x to the first power equals 1. Now what about n equals 2? Derivative of x squared. We actually calculated this earlier using the limit definition of the derivative, and we got 2x. Now we haven't done these other two, but we could find them using the same methods we've used before, using the limit definition of the derivative. And these are the formulas you would get. So based on these 4 cases, n equals 1 through 4, we want to try to generalize a pattern to say what is the derivative of x to the n. So notice in each case, whatever the power is, when you look on the right side, it's the coefficient in front of x, right? X squared, and then we have 2 in front of x. Over here, x cubed, and it starts with 3 times something. X to the 4th, we have 4 times something. X to the 1, we have 1 times something. So that's the first thing. The derivative of x to the n is n times something. Now let's look at the rest of it. When we start with x squared, on the right side we have x to the first power. When we start with x cubed, looking to the right, we have x squared. When we start with x to the 4th, over here it's x cubed. So you probably noticed that the power, the exponent value, decreases by 1 in every case. So that tells us for x to the n, on the right we're going to have x to the n minus 1. The power is decreased by 1. And so based on that generalization, we now have this formula for the derivative of any power function, x to the n. So the way you can think about this is you take the power, whatever that is, you bring it down in front, and then you reduce the power by 1. So this shortcut will let us take the derivative of any power function, x to a constant power, without having to use the limit definition, and we can very quickly find what its derivative is. Here's an example where we're going to be using the power rule to calculate these derivatives. So in part A, we're given f of x equals x to the 6th, and we want to find f prime of x. So applying our rule, you take the power, since this is a power function, x to a positive integer power, you just bring the exponent down in front, so you now have 6 in front, and then you reduce the power by 1, so the new power is 5. So we have f prime of x equals 6x to the 5th. So now you can see how simple and how quick that was to calculate that derivative by having this shortcut and not having to use the limit definition. Let's look at the next one, y equals x to the 1000. So we want to find y prime. You bring the 1000 down in front, reduce the power by 1, so now the power is 999. Third one, y equals t to the 4th, and this one we're using Leibniz notation. Notice it's dy over dt, right? Because when we see this formula, y equals t to the 4th, we know y is a function of t, not x in this case. So the independent variable is t, and the bottom of the derivative notation is always d of the independent variable. So this just says we want to find the derivative of this function. Because this is your variable t to a constant power, we can use the power rule. Bring the 4 down in front, reduce the power to 3. Third one, again it's a Leibniz notation. We're taking the derivative of the function in parentheses. And notice it's over dr, and that's because, you see, this is a function of r. Right? If we wrote the function by itself, it would be y equals r cubed. we didn't present it in that form. We just presented it as this is the formula we want to take the derivative of. So we know that because it's r cubed, we know it's a function of r, so that's why it says d over dr. Again, this is a power function, so you just bring the 3 down in front, reduce the power from 3 down to 2. Now the last one, we're back to the prime notation. We're given this g of x. Now this doesn't quite look like as simple as x to a power. So what we're going to do here is realize this is just 1/2 times x to the 4th. So then you can bring the 4 down in front when you take the derivative, but the 4 times the 1/2 becomes a 2. And then you still reduce the power by 1, so now it's x cubed. So this one I'm jumping ahead just a little bit because we hadn't dealt with having a constant in front. So we'll get to that soon, but you'll see that the same rule pretty much applies. You just carry this constant in front along with it. One other notational thing, since we started with g of x, the notation for the derivative is g prime of x. Whereas up here in part A, we started with f of x, the notation for the derivative would be f prime of x. The power rule that we just learned applied to functions that had the form y equals x to the n, where n was a positive integer. And we derived the formula based on that concept. But you can actually prove that the same formula holds if n is any real number. That means n could be a fraction or could be negative. And we have the same formula, derivative of x to the n equals n times x to the n minus 1. So here's some examples where we're going to use this formula. First we have f of x equals x to the 2/3. Notice the power n is a fraction, it's not a positive integer. So let's use the prime notation. So f prime of x equals, we bring the 2/3 down in front. Now we want to reduce the power by 1. So the old power was 2/3. We want to subtract 1 from that. So we'll simplify this by getting a common denominator of 3. We'll write 1 as 3 over 3. So combining that, we get negative 1 over 3. So the new exponent is negative 1/3. Let's go to the second one. This one doesn't look like x to a power, but I'm sure you're all familiar with the idea that the square root is the same thing as the 1/2 power. So we could rewrite that as x to the 1/2. So now we see we have x to a power. Even though the power is not an integer, we can still use the formula. Let's use the Leibniz notation here. So here we have y equals square root of x. That tells me y is a function of x. So in my Leibniz notation, I need to put y in the numerator, or dy, and then the x goes in the denominator as dx. Now, applying the power rule, we bring the 1/2 down in front. The new power, you take the old power, which is 1/2, and you subtract 1. So we'll get a common denominator by writing 1 as 2 over 2. And then doing the subtraction, we get negative 1 over 2. So that's the new power. And then the third one, we have z equals 1 over t cubed. This doesn't look like just a simple power function, right? It looks like 1 over a power function. But here, we can rewrite this fraction using a negative exponent. So here we have z equals t to the negative 3. Right? So that's a concept you should be familiar with from pre-calculus. Now let's find the derivative. Now here we don't have y, right? We have z as our dependent variable. So if we use the Leibniz notation, it would be dz over, notice the other variable is t, right? Z is a function of t, so the derivative notation would be dz over dt. And then because we have t to a power, we use the power rule. Even though the power is negative, the same rule applies. You bring the power down in front, reduce the power by 1, right? So the original power is 3, and we want to subtract 1 from that. So we get -4 for the new exponent. So that's these 3 examples illustrate some situations that you should be prepared for. One is if you have, well, a fraction as your power, you can still use the power rule, but especially in 2 and 3, because you have to take what's given and rewrite it as x to a power before you take the derivative, because the form they're given in is not the correct form for using the power rule. So if you can rewrite a square root as a 1/2 power. Similarly, you could rewrite a cube root as a 1/3 power. Right, so any root you can rewrite as a power. And then if you have a variable to a power in the denominator, you'll need to remember you can rewrite those using a negative exponent. And then once you get it in the form of a power function like this, then you just apply the power rule. In this example, we're asked to find an equation for the tangent line to the curve y = 1/x at the point 1, 1/4. So just a quick sketch to see what we're looking at. I'm going to first graph the curve y = 1/x, which is a familiar curve. It has these 2 separate pieces. So that's our curve y = 1/x in green. Now the point 1, 1/4 you can see is on this curve, because if x is 1, when you plug it into the formula, you get 1/4 for y. So that point would be somewhere around here. And so I'm going to sketch in the tangent line, and that's the line we're trying to find the equation of. Now to write an equation of a line, you have to have 2 pieces of information, slope and a point. So we need the slope of the line and a point. Now we already know a point, right? We were given that this tangent line contains the point 1, 1/4. So we've got that piece. So now we need to work on slope, and that's where we use the derivative. So we need to find dy dx. Now the function is 1/x. So we just saw an example similar to this. If we rewrite that using a negative exponent, it would look like x to the -1. And we recognize this as a power function. And so we can use the power rule to find its derivative. So the derivative notation would be dy dx, right? Because here, the way the formula was given, we can see y as a function of x. Using the power rule, we bring the power down in front, which is -1, and then reduce the power by 1. So the old power was -1. When you subtract 1 from that, you get -2. Now, if you want, you can rewrite this using the fact that we know a negative exponent means you could move it to the denominator and make the exponent positive. So that's dy dx as a function of x. Now to find the slope of the tangent, you have to tell it which point you're looking at, right? If you look at this curve, if you picked different points, you'd have a completely different tangent line with a different slope. So in order to find the slope of this particular tangent line, you have to tell it where you are, which point you're considering. And all you need is the x-coordinate of that point, which is clearly 1. So to find our slope, we're going to take our derivative, dy dx, and plug in the x-coordinate of our point, which is 1. Now I introduced this notation earlier, so we're using it again here. When you want to evaluate, when you're using the Leibniz notation and you want to indicate you're plugging in a number for x, this is how we do it. After the dy dx, you put a vertical bar, and down at the bottom you put x equals the number that you want to plug in. So when we plug in this number, we get -1 over 1 squared, which simplifies to -1. So now we know the slope is -1. So we have the two pieces we need. We have our point and our slope. The rest is just a matter of writing an equation of the line by using the point-slope form. So our tangent line in point-slope form, we take y minus the y-coordinate of your point, which here is 1/4, equals the slope, which is -1, multiplied by x minus the x-coordinate of the point, which is 1. So we have our equation now. It's just that we often like to write lines in the form y equals mx plus b. So let's do some simplification. Let's do two things. I'm going to add the 1/4 to move it from the left to the right, but I'm also going to distribute that -1 over the parentheses. So that gives us -x plus 1, and then here's the 1/4 that I added to both sides. And then one more step, we can combine the +1 and the +1/4. So we get y equals -x, and if you get a common denominator of 4, those two add together to 5/4. And that's the equation of the tangent line that I sketched at the beginning in red up at the top. We're going to develop some more rules that you can use as shortcuts for calculating derivatives. And these rules can be categorized as new derivatives from old. So the idea is, if you have a function that's formed from smaller functions, for example, two functions multiplied together, or two functions added or subtracted, that type of thing, we can find these formulas to find the derivatives of these more complex functions simply by knowing the derivatives of the smaller pieces. So the first of these rules is called the constant multiple rule. So here you're taking the derivative of a constant times a function. So notation-wise, what this rule says is you can pull this constant out in front of the derivative. So one way of thinking about what you're doing, the function you want to take the derivative of is actually a constant times some other function. What you can do is just first find the derivative of the function itself, and then once you have that computed, multiply the result by c. Or, here's a compact way of saying that, the derivative of a constant times a function is equal to the constant times the derivative of that function. And we'll practice some of these in a few minutes. In this example, we're going to use the rule that we just learned, the constant multiple rule. So in part A, we want to take the derivative of 3x to the fourth with respect to x. Notice this is a constant times a function. The function is x to the fourth, and we've got a constant in front of it. So the rule we just learned says in the Leibniz notation you can pull the constant out in front, and that's what we've written over here. So in the next step we just carry along the 3, and then we work on computing this derivative. Well, x to the fourth is a power function, so we can use the power rule to find its derivative. So we bring the 4 down in front, reduce the power by 1, and we get 4x cubed. Now we can multiply the 3 and the 4, we get 12x cubed for our final result. Now if you were using the prime notation, we don't view it quite the same. So in this case, let's say we had f of x equals the function we start with, the one we want to compute its derivative of. So f prime of x, right, we don't have that same notation to pull the constant out in front. So we think about it as what we did here. After we pulled the 3 out, we just carried the 3 along in the next step, and we've simplified the other part. So we're going to think the same way here. Just carry along this 3, and then take the prime of the function, right? The prime means the derivative. So I carry along the 3, and then the derivative of x to the fourth is 4x cubed, and then it simplifies to the same thing. Okay, let's go to part B. Here we're taking the derivative of negative x. Now negative means we're multiplying by -1. So that is a constant times x. So we can pull that -1 out in front. So here's where we've written it's -1 times x. Pull the -1 out in front. Now we're taking the derivative of x. We did this one earlier. The derivative of x is 1, but technically that does come from the power rule, because derivative of x, we can rewrite x as x to the first power and then use the power rule. So you bring the 1 down in front, reduce the power from 1 down to 0. Anything to the 0 power is 1 though, so this just simplifies to 1. So if you don't happen to have memorized the derivative of x as 1, you can just rewrite x as x to the first power and then use the power rule. So continuing on, that derivative got replaced with 1, and then we multiply these two. If we use the prime notation on this, we could say, let's let g of x equal the function we're starting with, which is -x. To find the prime, whatever constant is in front of your function, just carry it along. So carry along the negative side. And then, again, if it helps, write x as x to the first power. Then use the power rule. So bring the 1 down in front, reduce the power from 1 down to 0. We get -1 times 1, which is -1. So just a slight difference on how you write things if you're using the Leibniz notation or the prime notation. Now we have some more rules to add to our tools. The sum and difference rules. So here we've taken two simpler functions and we've added them together to create a more complicated function. And we want to find the derivative of that more complicated function. So this rule says it's equal to the derivative of the first function plus the derivative of the second function. So it's almost like you're distributing the derivative sign over the sum in the parentheses. And then the difference rule, similar, except we have a difference instead of a sum. And again, it looks like you just distribute the derivative over the parentheses. It's not really distributing in the normal sense because this is not multiplication, right? This does not mean d dx multiplied by the expression here. It means the d dx is a notation that means take the derivative of that expression. But an easy way to remember the rule is to view this like the distributive property. These can be extended to sums, any number of functions added together. And here it is written in the prime notation instead of the Leibniz notation. So you can distribute the prime to each term in the parentheses. So you eventually get f prime plus g prime plus h prime. So one way of phrasing the sum rule is the derivative of a sum equals the sum of the derivatives. So now we have the constant multiple rule and the sum and difference rules. I didn't present the proofs of these. All of these can be proved using the limit definition of the derivative, but just because of time constraints, we're skipping over those. You're welcome to read them in the book. And we'll get this way faster to applying these rules to calculating derivatives. So one of the main points of this section is how to find the derivative of polynomials. So now if for any polynomial you can apply the three rules we just learned to quickly find its derivative. The constant multiple rule, the sum rule, and the difference rule combined with the power rule. So here's an example to see how this works. Notice the function given here is a polynomial. Right, you learned about this type of function in pre-calculus. It's a sum of terms where every term looks like constant times x to a power. That's what a polynomial looks like. We want to find the derivative of this function, so let's use the prime notation. So f prime of x equals, now we can start applying these rules without writing out as many steps. The sum and difference rule basically says you can take the derivative of each term by itself and just keep adding or subtracting as you go. So I'll phrase that you can take the derivative term by term. Instead of viewing the function as a whole and finding its derivative all at once, we're finding the derivative of each term individually. And we know we can do that for a sum or a difference. So we would start with the derivative of 3x to the 5th. Now that has a constant out in front, but we know we can just carry along that constant using the constant multiple rule. So on the first term, we'll have carry along the 3, and then we need to find the derivative of x to the 5th. Well, that's a power function, so we use the power rule. Bring the 5 down in front, reduce the power down to 4. Now we go to the second term, the minus 6x cubed. Carry along the constant, the minus 6. Now take the derivative of x cubed. So we bring down the 3, reduce the power to 2. Going to the next term, we keep the plus 8, carry along the constant. Now the derivative of x squared, we bring the 2 down in front, reduce the power to 1. So it's x to the first power, we can just write x. Next term, carry along the minus 9. Now we need the derivative of x. We saw that recently, it's 1. Right? If you don't remember that, you just remember how we did it last time. We rewrote x as x to the first power and then used the power rule. Last term is the constant. The derivative of a constant, we saw that at the beginning of this section, it's always 0. No matter what the constant is, its derivative is 0. Now the rest is just simplifying. So we have 15x to the 4th minus 18x squared plus 16x minus 9. And now we have the derivative of this polynomial. So any polynomial, if you want to find its derivative, this is the process that you'll use. And once you've done enough of these, you could actually skip the step I wrote here, and you can just look at the function and go directly to here. So for example, on the first term, you'd say, well, I'm going to bring down the 5, and then go ahead in the same step and multiply it by the 3. So that gives you the 15. And then you reduce the power from 5 down to 4. And then on this one, you're bringing down a 3, go ahead and multiply it by the minus 6, that gives us minus 18. Reduce the power by 1, and so on. So as needed, go ahead and write out this middle step, and then get to here, but eventually you'll get comfortable enough with these that you can just go straight from f to what the simplified f prime. Now we've learned the shortcut for computing derivatives of polynomials, so we'll move on to our next type of function, which are exponential functions. Those have the form f of x equals a constant b to the power x. So before we go forward, I just want to point out that you cannot use the power rule on these. Even though it looks like the same form, something raised to a power, we can't use the power rule. So this is, if this is your f of x, this is not true that the derivative would be found by bringing the power down in front and reducing the power by 1. So make sure you know the difference, right? The power rule applies if the variable x is in the base and it's raised to a constant power, for example, x squared or x cubed. This has the reverse situation. The variable x is in the exponent, and the base is a constant. Because this is not a power function, you can't use the power rule. So we need to develop a new rule for these exponential functions. So we'll go back to our limit definition of f prime, which is copied. We've seen that before. Now we're going to start substituting in. So for f of x plus h, we go to our formula for f. Wherever we see an x, we replace it with x plus h. So it's b to the power x plus h. And then we have minus f of x, so we can just use b to the x. We still have the limit, same denominator. The next simplification, we're going to use a property of exponents. When you have a sum in the exponent, you can write it as b to the first times b to the second. Right, we're used to using this rule reverse. If you started with this, the rule we're familiar with is that you would add the exponents and write that as b to the x plus h, which we wrote here. Everything else is still the same. That was the only simplification we made. The next thing is, if you look in the numerator, both terms have b to the x, so that can be factored out. So here we pull that out in front. In the first term, after we pull that out, we're left with b to the h, and in the second term, we're left with minus 1. So here's what remains after we factor out b to the x. Now the next step has to do with the fact that if you look at this expression, we see three different letters, b, x, and h. But in terms of the limit, h is the variable, right? H is the one that's approaching something. So the b and the x are like constants from the viewpoint of this limit. So that means anything, if there's like this b to the x, is just like a constant in terms of the limit. And a constant times a function, we've learned that property that you can pull that constant out in front of the limit. And that's what we've done down here. So now we're still not done because we still have a limit here to evaluate, but we've simplified from our original definition of the derivative down to this. So we're going to pick up with this on the next slide. So we're looking at this exponential function, y equals b to the x. We applied the limit definition to calculate f prime of x, and on the last slide we got it simplified up to this point. So we're going to pick up from here. So we're actually going to find this limit using a very different type of strategy. We're going to first calculate what f prime of 0 looks like, and we'll actually show that f prime of 0 is equal to this limit. And that'll allow us to replace this limit with f prime of 0. So I'm going to add a little work to what's already here. To find f prime of 0, right here it's not f prime of x, it's f prime of 0. So you just take the formula for f prime of x, but where we normally write x, we're going to replace it with 0. So normally in the numerator here you have f of x plus h, but we're replacing x with 0. And then you have minus f of x, we replace that x with 0. And then denominator h. Now think about what f of 0 plus h would look like. From over here, it's b to the 0 plus h, which is b to the h. What would f of 0 look like? It would be b to the 0, which is 1. So now that explains exactly where that comes from. And as we started at the beginning, this is f prime of 0. So, like I was saying a minute ago, that means this limit here is equal to f prime of 0. So what I'm going to do now is rewrite this equation for f prime of x equals b to the x times, and then replace this with f prime of 0. And that's what we've written here. We just flipped the order. We put the f prime of 0 on the left. So we've now got this expression for f prime of x. And we can conclude from this, right, the original f of x was b to the x. F prime of 0 is some constant that we don't know yet. But what this tells us is that the derivative of b to the x is just a constant times b to the x. Right? So if we put this into Leibniz notation, it makes that statement a little more clear. If we take the derivative with respect to x of this exponential function b to the x, we get this constant f prime of 0 times b to the x. Whenever we have a constant times something, we say it's proportional to that thing. So the derivative of b to the x is proportional to b to the x. In other words, it's proportional to itself. Now the value of f prime of 0 will depend on what b is. So for example, this could be 2 to the x or 3 to the x or 12 to the x. That will determine, whatever that base b is, that will determine the value of f prime of 0. So we'll explore this more in the next slide. So we've developed this formula down here for f prime of x if your f of x is this exponential function b to the x. And we were discussing that this f prime of 0 will be different depending on what exactly the f of x looks like, right? So I guess we didn't write it in here. We're dealing with f of x equals b to the x. So we're going to consider some different values for b and figuring out what f prime of 0 would be. So let's consider b equal to 2. So that means our function that we're considering is f of x equals 2 to the x. That's our exponential function. So let's calculate f prime of 0. So we just use this formula that we derived on the previous slide and plug in 2 for b. So it will be the limit of 2 to the h minus 1 over h, which we've written here. Now the problem is the methods we've learned for evaluating limits don't help us on this, right? We can't use direct substitution because we get a 0 in the denominator, and there's no factoring that's going to help us cancel the h. So we're just going to guess the limit by creating a table, which we've done this kind of thing before. So since h is approaching 0, we want to start by choosing numbers for h that get closer and closer to 0 as we go down the rows. And over here, we've calculated this expression here. So for example, when h is 0.1, we plug that into this formula in a calculator and we get this number. And then we go to the second row, we plug in 0.01 into here, calculate a number, continue all the way down. So our question is, as h goes to 0, which means as we're moving down the rows, what are these numbers approaching? And it's hard to tell exactly, but it looks like it's around 0.693. So we just approximated that as 0.693. Now we want to go to a different b, so we decided to choose b equal to 3. So that means we're considering the function f of x equals 3 to the x, a different exponential function. And again, we want to figure out what is this value of f prime of 0 for this b. So we'll use this formula here, but this time we'll plug in 3 for b. So it now looks like this. Again, we don't know, our methods don't work for evaluating this limit, so we'll just use the table. We choose h's that are progressively getting closer to 0, and then for each one of those h's we calculate this expression. So just like before, take your h, plug it in here, calculate an output. And then we ask the question again, as h goes to 0, meaning as we move down the rows, what are these numbers approaching? And we could estimate that as 1.099. So now putting some pieces together, this is the formula we derived on the previous slide for the derivative of b to the x. So if we apply that to these two cases, so let's start with 2 to the x. When we take the derivative of 2 to the x, we get f prime of 0 times 2 to the x. And we determined f prime of 0 is approximately 0.693. So the derivative of 2 to the x is this constant times itself, 2 to the x. Now I'll apply the same method to find the derivative of 3 to the x. So the derivative of our exponential function is always f prime of 0 times the original function. So here it'll be f prime of 0 times 3 to the x, because our original function is 3 to the x. The f prime of 0 for the case when b is 3 is this other constant, 1.099. So the problem is these aren't exact, right? We guessed these limits, and they're probably rounded off. And the other problem is you have to find a new formula every time. So if it's 2 to the x, or 3 to the x, or 4 to the x, every time it's a different constant. And so it's not like one formula that applies to all cases. So we're still going to keep working on these to see if we can address those issues and find a more precise formula that will work in all cases for all exponential functions. We just found these formulas for the derivative of 2 to the x and the derivative of 3 to the x. So we saw that in all cases, if you have an exponential function b to the x, the derivative is always some constant times the original function, right? Over here, the same thing with 3 to the x, the derivative is some constant times 3 to the x. The simplest case would be if that constant were just 1, because then you would have the derivative of your exponential function just equals the same thing as the original exponential function. And notice that the two cases we looked at, the constant here is less than 1, and for 3 to the x, the constant is greater than 1. So probably if we chose a base somewhere between 2 and 3, and we calculated the f prime of 0, which is this constant, for that base, we would get 1 as long as we found that right constant, some number between 2 and 3. Here's a graph that illustrates this. So in blue, this is the graph of 2 to the x, and this dark, I guess that's purple, is 3 to the x. Now f prime of 0, remember that's this constant out in front is the f prime of 0. What does that represent in terms of the graph? Well, we know f prime is the slope of the tangent, and we've plugged 0 in, so it means if you go to x-coordinate 0, find the corresponding point on the graph, sketch the tangent, f prime of 0 is the slope of that tangent. So now let's apply that to the graph 2 to the x. F prime of 0, if you imagine the tangent here to the blue graph, the slope of that tangent would be this number 0.693. Now if you go to the purple graph and sketch its tangent, you can see it's steeper. And we calculated that slope to be 1.099. So again, that makes sense. There must be some exponential function in between those two, which we've sketched here in red, where the slope of the tangent is exactly 1. That's what we're looking for. This is going to be like our ideal case. So what we do is we define E to be that base. So E is the base. So if you look at y equals e to the x, the constant that goes in front, which is the f prime of 0, the slope of the tangent at that position, would be 1. So what we do here is this is the equation for f prime of 0 using e in place of the base b. And we define e to be the number that makes this limit equal to 1, right? This is the f prime of 0 formula. Okay, so you may have heard of this number e before. E is an irrational number, so it's kind of like pi, meaning if you wrote it out in decimal form, it continues forever with no repeating pattern, and we can write out the first few decimal points. It starts with 2.71828, and it continues forever, just like pi, with no repeating pattern. So anyway, our conclusion is e, if we look at y equals e to the x, and actually if we maybe it'd be better to call that our f of x, then the derivative at 0 for that function would be the number 1. And so our main conclusion, which we'll put on a future slide, is the derivative of, if we looked at e to the x instead of 2 to the x, it would equal 1 times e to the x. So that's going to be an important rule. We'll write that on its own formula on the future slide. So we'll summarize what we just discovered. If we take our exponential function b to the x and we use the number e in place of b, so the base is e, and we plug all, so we just determined for e, we have e to the x, we have f prime of 0 is 1. We also had this formula for the derivative of any base b to the x to be f prime of 0 times b to the x. So now applying that to the case where the base is e, we get the derivative of e to the x is 1 times itself. So this is a really easy rule to remember. We now know the derivative of the exponential function e to the x is equal to itself. And this is the only function that has this property, that the derivative of the function is the same as the original function. In this example, we're asked to find the derivative of the given function. Notice the function is a sum and difference of 4 terms. So first we could think of the sum rule, where we can just take the derivative of each term individually. So we're going to go one at a time. Now notice the first term is a constant times an e to the t. So first, I guess before we do anything else, because we see the two variables are y and t, when we start writing our derivative, if we use the Leibniz notation, it would be dy dt. If we use the prime notation, we would just call it y prime. Now, start with the first term, 3e to the t. That's a constant times e to the t, so we can use the constant multiple rule. You just carry along the constant, and now we multiply that by the derivative of e to the t, which is just e to the t, right? The derivative of e to the t is itself, and that 3 just gets carried along in front. Now we go to the next term. This is a power function, right? Make sure you see here the difference. An exponential function has the variable in the exponent and a constant base. This is the opposite. The variables in the base and the constants in the exponent. This is a power function, so we use the power rule on it. So we bring the 2 down in front, which gets multiplied by the minus 5. So now we have minus 10 in front, and we reduce the power from 2 down to 1. The next term is 3t, right? That constant 3 just gets carried along. The derivative of t is 1. So 3 times 1 is just 3. I guess we could write that in here. Now we have the derivative of 8, right? 8 is a constant, so its derivative is 0. And so let's just simplify and get our final answer here. 3e to the t minus 10t plus 3. So you can see how simple this was to compute this derivative using these laws that we've learned, these shortcuts. Imagine trying to apply the limit definition to this complicated function. To find the derivative using that limit definition would be incredibly difficult, and you can see how easy it was to apply the shortcut. We're given the function f of x equals e to the x minus x. And we want to find the first and second derivatives, and then we'll do some graphing. So this first problem is similar to what we saw in the last example, finding the derivative of this. So here we've written f prime of x, but then we just switch over to the Leibniz notation. You don't have to do that, but we chose to do that here. So we have the derivative of the given function, which is a difference, and we know we can split that up over the difference. So derivative of the first term minus derivative of the second term. We just learned the rule for the derivative of e to the x is itself. And then we've seen earlier the derivative of x is 1. So this is our formula for f prime of x. Now to find f double prime of x, we're going to take the derivative of f prime. So in Leibniz notation, that means we're taking the derivative with respect to x of, this is the formula for f prime. Again, we have a difference, so we can split the derivative up to each term individually. And then we know the derivative of e to the x is itself, and then 1 is a constant, so its derivative is 0. So minus 0, which we don't have to write. So now we found f prime and f double prime. So we'll do the graphing on the next slide to compare the graphs of f and f prime. So we were given this function f of x equals e to the x minus x, and we computed its derivative already and got e to the x minus 1. So over here we've used a computer to graph these two formulas. So when we graph this formula for f, we get this blue curve, and then graphing the formula for f prime, we get this red curve. So we can now compare these and see the kind of relationships we've already talked about between the graph of a function f and its derivative. So if we pick some interesting points, like right here at x value 0, on the graph of f it looks like we have a horizontal tangent. So that means the slope of the tangent is 0, which means the value of f prime should be 0. Right? This point here has y coordinate 0. If we pick points on the left half of the graph, notice the tangent lines are decreasing. They have negative slopes. So that means f prime should be negative when we're on the left half of this graph. And you can see these are negative y values. When we look at the right half for x greater than 0, if you pick any point here, the slopes are positive. That means the values of f prime should be positive. And if you look at this piece here on the right half, the pink graph has all positive y values. So we're seeing the same relationships that we've seen before. They should always be true when you look at a graph of a function and its derivative. In section 3.1, we learned some shortcuts for finding derivatives of polynomial and exponential functions, but there are still a lot of other types of functions. So a common situation that we see is a function that's actually consists of a product. So you might have two functions of x multiplied together to create a more complicated function. So we want to know how to take the derivative of that type of product. Similar for a quotient, we could have a function that's defined as a fraction with a function of x over a function of x. And we need to develop the rules to tell us shortcuts for computing derivatives of these types of functions. And that's what we're going to do in this section. We're trying to develop a rule first for the derivative of a product. So what we're actually considering here is if you have two functions multiplied together and we want to compute the derivative of that product. So it's natural to guess that this would be the same as f prime times g prime. And Leibniz, one of the founders of calculus, made that guess also. But it turns out that's not true. Okay, so I'm going to put an X here. This is not true. Now let's verify that it's not true by considering an example. So look at this example. F of x is x, g of x equals x squared. So we're going to compute, we'll try out this rule. We'll calculate the two sides individually, and we'll see that they're not the same. So we'll actually start with the right side. So let's first find f prime and then find g prime, and then we'll multiply them together. So it's easy to calculate f prime is 1 and g prime is 2x using the power rule. So we have those two pieces. So if we go ahead and multiply those, we get f prime times g prime would be 1 times 2x, which simplifies to 2x. So that's what we get for the right-hand side. Now let's do the left side. So this says first multiply f and g and then take the derivative. So when you multiply f and g, right, just to explain where this comes from, it means x times x squared, which gives us the x cubed that we see there. So first we multiply f and g, we get x cubed, then we take the derivative of that. So using the power rule, the derivative would be 3x squared. So for the left side, we get 3x squared. For the right side, we got 2x, right? They're different. So we got a different result when we did these two separate calculations. So that tells us that these two things are not equal. So our intuition doesn't work here, right? The derivative of a product is not the product of the derivatives. So we're going to look at finding a formula that will work to tell us how to find the derivative of a product, and that'll be our first goal in this section. We just saw our initial guess for how to take the derivative of a product was not correct. And Leibniz made the same mistake. It was his first guess also. And as soon as he realized it didn't work, he discovered the rule that does work. So we're going to call this rule the product rule, but first we're going to kind of try to derive it ourselves before I present it. So we'll start by taking our two functions, f and g, that we're going to multiply together before we take the derivative of that product. And we'll define u to be f of x, v to be g of x. So one way to interpret their product is the area of a rectangle. So this white rectangle here has dimensions u by v. So its area, of course, would be u times v. So the product of the two functions is represented by the area of this white triangle. We've seen in the definition of the derivative that you have to consider f of x plus h. Instead of calling it h, we're going to call it delta x. That represents some small increment in the x direction, but it's the same idea as what we've been calling h. So we're going to think about our rectangle now. What would happen if we changed x by adding delta x to it? So that means u and v would both change, right? Because u is a function of x, v is another function of x, right? F of x and g of x. So how much would the area change? Well, first we'll find how much u and v change. So delta u is the amount that u changes, would be f evaluated at the new x value minus f evaluated at the original x value. So it's just the u value at the end of the shift minus the u value at the start. And then we do the same thing for v. How much v changes? Remember, v is defined to be g of x. So the ending value of g would be g evaluated at x plus delta x. And then we subtract from that the value of v at the beginning, which was g of x. So now we have these new values, the amount that u and v changed. So the new product, let's think about that now. It would be the shifted value of u, right? The value of u at the end, which is u plus the amount that it changed. And then we multiply that by the new value of v, which is the original v plus the amount that v changed. This product is the new product. And in terms of our rectangles, we can see we've added this increment to u, right? This was the original u. We've added this increment to it. And this was the original v. We added this increment to it. So now we have this bigger rectangle is now representative of where we are in terms of the lengths after we changed x by adding delta x to it. So what we want to do now is figure out how much did the area change. Right, so we've looked at lots of changes. X changed by an increment delta x. That caused u and v to change. Right, u changed by an increment delta u, v changed by an increment delta v, which we've calculated here. And then, in turn, the area of the rectangle would change. Right, the original area was this white region. Now the area is this bigger rectangle. So let's find how much the bigger rectangle changed. So this delta uv, that means the change in the product. So what we do is we take the new area, let me label that. This is the area of the bigger rectangle after the increment, minus the original area before we changed x. So now let's do some simplification. Let's start by just multiplying out this product here using FOIL. So we have u times v, but notice that's going to cancel with this minus uv. And then for the outer terms, we have u delta v plus v delta u, which we see here, the first two terms. And then for the product of the last, delta u times delta v, we see here. Okay, so there were actually 5 terms once we write all this out, but the uv and the minus uv canceled, so there's only 3 terms remaining. So this represents, again, the change in the product. Now we can interpret this on the rectangle here as these are 3 areas that are shaded. Look at this one, u delta v. This is length u, this is length delta v, so the area here is u delta v. This product, v delta u, is this area, right? Because this height is v from over here, and this distance here is delta u. And then the third increment, or the third term here, is delta u delta v. That's this rectangle, because of the dimensions here, delta u, and that dimension is delta v. So we've now interpreted the change in area as being the sum of these 3, and that makes perfect sense, right? Because the original area was the white one, the new area is the bigger one, so the amount that it changed would naturally be these 3 shaded regions. On the last slide, we developed this formula here for delta uv, right? The change in the product. We need that because we're wanting to find the derivative of uv. And that involves first finding the change in uv over some small increment in x, and then taking the limit as that increment goes to 0. So let's continue from here. The next step is to divide both sides of this equation here by delta x. Remember, delta x is like the h, and we know we need the h in the denominator of our expression before we take the limit. So here, the left side, we just put over delta x. And then for each one of these, we put each of these 3 terms over delta x. And on some of that, we pulled some of the terms out in front, out of the denominator, and put them in front. So then, to get to the derivative, we need the limit of this. This is like change in y over change in x. The derivative is the limit of that quotient, that difference quotient. So when we take the limit of the left side as delta x goes to 0, that becomes the derivative of the function in the parentheses. So we have derivative of uv. The dx means that it's with respect to x. Now on the right, So that's kind of what we have here. That's just showing that extra step. Now we take the limit of this side also. And so all we did here is the limit as delta x goes to 0, and then we copied the right side exactly as it is. So the rest is now evaluating this limit. So we're going to use properties of limits. So first of all, we have limit of a sum. So we can split that limit up to each term individually, which we have here, those three separate limits. But we've also used some other limit laws. For example, here, the limit of this product so technically it would be limit of u times the limit of this other term. But the limit of u, remember it's really u of x. And since there's no delta x inside the u, it's just u of x, and since delta x isn't in it, in terms of this limit, u of x is a constant. So the u can be pulled in front of the limit, and then we still have the limit of the second term in that product. We did the same thing. I just noticed there's a typo there. This should be a v. Okay, then we did the same thing here, limit of this product. We can pull the v out in front because there's no delta x. And then we still have limit of the second term in the product. And then for the last one, these are both referring to the incremented values. So all of these depend on delta x. So we can't pull either of these out in front of the limit. So we have to just take limit of the first times limit of the second. So continuing on, this limit here is exactly the definition of the derivative for v as a function of x. So that limit is just the definition of dv dx, right? The derivative of v with respect to x. And we just keep the u in front. For the second one, we keep the v in front. And then this limit is exactly the definition of u with respect to x. So we call that derivative du dx. Now the third, we have two limits to compute. So first of all, let's think about the limit of delta u. So remember, delta u is the increment in u. It's how much u changed when we changed x. But if we let the change in x go to 0, that means there's essentially no change in x by the time we get really, really close to 0. So if we don't really change x, then we don't really change u either because we haven't incremented the x. And that depends on u being a continuous function. But so this limit actually equals 0, so we've replaced that here. And then the second limit, because it's a limit of one of these delta something over delta something, that's the definition of the derivative. In this case, derivative of v with respect to x, which we write as dv dx. So this whole third term, it becomes 0. So we end up with the derivative of uv with respect to x equals the sum of these two terms, and I've copied that down here. So this is one way to write the product rule. This is the version using the Leibniz notation. We'll show the version using the prime notation on the next slide. Okay, so here's how we can think about this. The derivative of u times v. I'm going to refer to u as the first function, v as the second function. So on the right, we have first function times the derivative of the second function plus the second function, v, times the derivative of the first function. So in shorthand, we often say first times derivative of the second plus second times derivative of the first. So that's our product rule, and you can see it's different from our first guess, right? Our first guess was the derivative of u times v. should be the derivative of u times the derivative of v, and that's clearly not what this product rule says, right? This formula here is the correct way to take the derivative of a product. So to summarize what we got from our derivation of the product rule, this is the way we wrote it on the previous slide. But remember, in this derivation, u was equal to f of x and v was equal to g of x. So another way to write it is to make those substitutions. So we have d dx of f times g. So we've written it that way here. And on the right, replaced u with f, replaced v with g. And same thing here, dv dx is the same, since v is the function g of x, we can write it like this, derivative of g of x with respect to x. And since u is equal to f of x, we can write this derivative as d of f of x over d of x. So this just shows it in terms of the original function names. And then here it's written with the prime notation, right? This prime means the derivative of f times g. And over here we wrote it in the same way as above, first times derivative of the second plus second times derivative of the first. Here's some examples where we're going to compute the derivative of some products. So our first function, you can see it's written as a product of two functions. Right, so the common mistake, I'll go ahead and write it out so you can see it and not make that mistake, is to say, so this is the wrong way to do this, is to say f prime of x equals the derivative of the first factor multiplied by the derivative of the second factor. And so continuing on with this, you would get, for the first derivative using the power rule, 3x squared minus 2, and then we multiply that by the second term, which is the derivative of this other expression. For that, we get 12x cubed minus 8x. Okay, so that is wrong, right? So it's easy to make that mistake because that seems like how the product rule should work. But we know there's another formula for this, so let's do this the correct way now. So to find this derivative, we first observe that f is a product of two functions of x. So using our product rule, we start with first times derivative of the second. So first is the first set of parentheses, x cubed minus 2x, multiplied by derivative of the second. So I've used the Leibniz notation to show derivative of the second term. We haven't computed the derivative yet. I just put the notation that says we need to. And then we do plus the second function multiplied by derivative of the first function. So we're not done until we compute these two derivatives. So let's continue on. So we'll keep this first expression the same. Now the second expression says take the derivative. So taking the derivative of what's in the parentheses, we get 12x cubed minus 8x. Continue on, we have plus, keep the next part the same. And then we multiply that by the derivative of what's in the next parentheses, which is 3x squared minus 2. This is the correct formula for the derivative. Now, of course, you could simplify a lot by distributing and combining like terms, but we're not going to do that right now. That would be pretty involved. The main thing is we now have a formula for the derivative. So let's go to the second one. Here we have x cubed times e to the x. So the key thing is you have to recognize this is a product of two functions of x. The first function is x cubed, the second function is e to the x. So just to emphasize again, let's go over the wrong way to make sure we don't do this. And that would be to just say derivative of the first times derivative of the second. And then when you compute those derivatives, you would get 3x squared multiplied by, and then we know the derivative of e to the x is just e to the x. Okay, but that's wrong. So now let's do the correct way. So g prime of x equals, so we take first, which is x cubed, times derivative of the second, which is e to the x, plus second, which is e to the x, times derivative of the first, which is x cubed. Now we have two derivatives to compute, so we do a simplification. So we have x cubed times, so we know the derivative of e to the x is just e to the x. And then continuing on, we have plus e to the x. Now we need to take the derivative of x cubed, so we use the power rule. We get 3x squared. Okay, so that's our formula for g prime of x. This example, we're given this function f of x equals x e to the x. We want, in part A, find its derivative. And then in part B, we want to find the nth derivative. So we're really generalizing in part B. So first of all, just to find f prime, the first thing is it's really important you recognize that this is a product of two functions of x. That's what tells you you have to use the product rule. So following the product rule, we're taking the derivative of the given function. The first is x, the second is e to the x. So we start with first times derivative of the second. Then we have plus second, which is e to the x, times derivative of the first, right? The first is x. In the next step, we compute these two derivatives. So we keep this x. We know the derivative of e to the x is e to the x. Then we have plus e to the x, just copy that. And then multiply by the derivative of x, which we've seen before, is equal to 1. So you could stop here, but they did a simplification here by factoring out e to the x. So that leaves x in the first term and plus 1 in the second term. So we could write the simplified version like this for f prime of x. So now in part B, we're going to look at some of the higher derivatives. We just calculated the first derivative of f to have this formula here. Now we want to generalize to say what the higher derivatives would look like. So we'll start by finding the second derivative, then we'll look at higher derivatives than that. So to find f double prime, we need to take our function f prime that we've just found and then compute the derivative of that. So here we've said f double prime of x equals the derivative of, notice what's inside here is f prime. Notice that this expression inside the brackets is a product of two functions of x. So x plus 1 is the first term, e to the x is the second term. So then, because it's a product, we'll use the product rule here, and we'll say first times derivative of the second. So there it is here, plus second, which is e to the x, times derivative of the first, and that's now written here. Next step, we'll compute these two derivatives. So we keep the x plus 1. Derivative of e to the x is e to the x. Then we have plus, keep the e to the x. Now take the derivative of x plus 1. Well, we can go one term at a time. So first of all, the derivative of x is 1. Then we have plus the derivative of 1. But since 1 is a constant, we know its derivative is 0. So we get 1 plus 0 for the derivative, which is just 1. And then simplifying, it might help to show one more step here. So if we distribute, we get x e to the x plus 1 e to the x. That comes from distributing this e to the x over the parentheses. And then after that, we have plus e to the x. Now we've got three terms, and they all three of them have e to the x. So now you can factor e to the x out, and that leaves x plus 1 plus 1, which is the same as x plus 2. So we have the e to the x factored out, and what was left in the parentheses was x plus 2. So now we found a formula for f double prime. What would f triple prime look like? Well, you'd go through the same process, but you would start with this formula, which is f double prime, and compute the derivative of that. And because this is a product, you'd have to use the product rule. So we're not going to show that work here, but it's going to be similar to what we did here for f double prime. When you simplify, you'll get x plus 3 times e to the x. And then to find the fourth derivative, you would start with this formula for f triple prime and compute the derivative of it. Because this is a product, you'd have to use the product rule. And you'd get this. Now I want to point out the notation. We could have called this f with 4 primes. But once you get to 4 or more primes, it starts to get to be a little too much to write those individual primes. So this is now rewritten. Just an alternate notation is to put the superscript is a 4 in parentheses. That means the same thing as an f with 4 primes, right? Both of those represent the fourth derivative. And you could do that for the third derivative if you wanted. You use parentheses 3, but often most people are okay with 3 primes, so we'll often write 3 primes. Okay, so when you compute the fourth derivative, we get this formula. So now the question is, what would the nth derivative look like? Well, look at the pattern. So here's the first derivative. Now compare that formula to the formula for the second derivative, and then the third derivative, and the fourth derivative. They all look the same except for this constant that's added to x. And you probably noticed if it's the fourth derivative, it's a 4. When it's the third derivative, it's a 3. Second derivative, it's a 2. First derivative, it's a 1. So if it's the nth derivative, that would be an n. So you'd have x plus n in parentheses times e to the x. So there's the formula. We could generalize from our pattern to get this. And notice it uses that new notation because we don't know what n is. It could be any integer. So we can't use the primes since we wouldn't know how many primes to make. Okay, so this formula works for any positive integer for n. It will tell you what the nth derivative of this function would look like. Right? If you wanted to know the 100th derivative, all you do is plug 100 in for n here and you have it. Saves a lot of work from calculating the derivative 100 times, right? Going through first, then second, then third, all the way to 100. Now we'll summarize what we talked about today. So we covered all of section 3.1 where we learned shortcuts for finding derivatives of polynomials and exponential functions. We worked our way up to polynomials, first by learning the derivative of a constant function is always 0. Then we learned the power rule, so we could take the derivative of any function of the form x raised to a constant power. Then we learned some rules to tell us how to take the derivative of a constant times a function, the sum of two functions, or the difference of two functions. And if you put all those rules together, we now have a method for taking the derivative of any polynomial without having to use the limit definition of the derivative. And then we derived a rule for the derivative of exponential functions, which have the form a constant raised to a power x. Now in particular, we learned the derivative of e to the x, right? E is that irrational number we talked about. The derivative of e to the x is equal to e to the x. We talked a little bit about other exponential functions where the base is any number, so like 2 to the x, 5 to the x, 12 to the x. We haven't completely developed the rule yet. We've got it partially there, but we'll get to the complete version of the derivatives of those later. Then we started section 3.2. So here we're going to learn rules for the derivative of a product of two functions or the quotient of two functions. And so far we learned the product rule, which tells us how to take the derivative of a product of two functions.